was much larger.
We can estimate how big the flare on DGCVN was with respect to the solar scale. It would have been an X 100,000. So this is several orders of magnitude larger than the biggest solar flare we've ever seen. The flare that Swift triggered on from DGCVN was only the beginning of what turned out to be a fairly extended series of flares, a flare event, if you will, that lasted almost 20 days.
This was a very different star than the Sun, so we don't really have to worry about this happening in the present-day Sun. The young Sun, such large events may have occurred. In the present-day Sun, the activity levels are much lower. And the fundamental reason that DGCVN is more active in the Sun is it's a very young star, 30 million years. It's rapidly rotating. Young stars are born that way. And rapid rotation is one of the key ingredients which powers activity. The faster the rotation, the greater the activity.
While not a threat to us, the massive flares of red dwarf stars can help us better understand the flares produced by our own Sun. They are also of interest because red dwarf stars are often orbited by planets. Some data suggest that 40% of red dwarfs have super-Earth-type planets orbiting in a habitable zone, where liquid water is possible. If this is true, then they are good candidates for supporting life. However, the habitable zone around a cool, dim star like DGCVN is much closer to the star than the Earth is to the Sun.
When planets are closer to their star, they're more susceptible to anything the star does. For instance, if the star flares, the planet is much closer to the star and it can be hit by the radiation or the particles that get ejected from the star when this flare process happens. If you happened to be on a planet around an M dwarf when one of these large flares went off, you'd be having a very bad day.